Hi everyone, this is Mahesh. Hope you are doing good. This is a new series on sorting techniques. So in this video we will learn about selection sort. So this is a slow sorting technique, but it is important to understand this sorting algorithm because this is the basic sorting technique one can use. Mostly for the large input this sorting technique is not really recommended because we will see why we don't recommend because it takes more time to sort the numbers. So when we talk about sorting, so sorting is basically sorting of numbers in ascending or descending order. So let us look into the selection sort in this video. Let us start with selection sort. So selection sort, so basically what it does is, it is, as I was saying, it is a simple sorting technique where we look into numbers and we will pick the minimum number and we keep on adding it to the start of the array. So let us take an example. Let us assume we have an array A. Maybe there are some examples: 21, 15, 7, 8, 3, 5, maybe 6 numbers. So like this. So if you look into this array, so on the naked eye, if we want to sort it, how do we do? I will first take 3 and I will then take 5, I will then take 7, 8, 15 and 21. So that is the way we keep sorting in the ascending order. If it is descending, then we will take the maximum element first. That is the difference. So how do we achieve this technique? So basically what I do, I will place a pointer here. This is the first element I want to get, and I will scan throughout the remaining elements. So which is minimum here? So 3 is the minimum element. So what I will do, I will simply, maybe I will keep that as it is. I will simply swap that number. So I will keep 3 here, then I will keep 21 and remaining numbers as it is. So now this position is sorted. So this position is sorted at this point of time. So we normally call it as first pass because we are trying to sort or keep the element, the first element sorted. So this is normally we call it as passes. So this is the pass 1. So in pass 1 we arrange the first element in the array. So now next thing is, so one more thing. So at this point, this particular block is sorted one, but this one we don't know. It is still unsorted. Okay. So now what I do, after first pass, again I'll give this input to the second pass. So in the second pass what happens, again I'll keep this pointer here because this is the place where I want to sort my next element, and I will keep scanning. So which one is smaller? This is smaller. So I will take this, I'll swap it here. So I'll keep 5 there and 15 here. Now at the second pass, this much is sorted. So towards left it is sorted, towards right it is unsorted. Now my next thing, I will keep the pointer here. I will search for the minimum number. So this is already the minimum number, so there is nothing to swap. Then this block is sorted, this is unsorted. Now again I will keep the pointer here. I'll search for the minimum number. So this is already the minimum number, so there is no need to swap. So I will move the pointer to the next index. Then till this it is sorted, and out of remaining 2 elements this is smaller. So what I will do, I will simply swap it. So 15 comes and sits here, and 21 sits at the end. We don't need to sort this number because already it is sorted and it is in its correct position. So there is no need to sort this element. So what we did, we started from the first index. Let us assume these are the indexes. So in real-time scenario, I mean, it is a zero-based indexing, but here we will, I mean, simply for the understanding purpose, we will consider as one-based indexing. So what we did, we started here and we ended at this n minus 1th index. So basically what I'm trying to say, we involve n minus 1 passes to sort this particular entire array. So that's what this sorting, I mean, that's how this sorting works. Now let us try to understand this pass wise. So assume this is our pass 1 and this is our input. So we have 21, 15, 7, 8, 3 and 5. Now I will keep the pointer here. I'll keep scanning from here. So let us assume, let us take the index, minimum index. So why, I will tell you. So you will eventually understand. So I will assume this is my first, this is my minimum index. So what I will do, I will keep minimum index as 1. Now what I will do, I will scan the next element. So is 15 less than the element at minimum index? That is 1 for now. Yes. So I'll update this minimum index. Now it becomes 2. Now I will move to the next element. This one I'll keep it in this place, but I'll scan through the remaining elements. So next 7. 7 is less. So I'll update minimum index. Next 8. 8 is not less than 7. So I don't update. Then 3 is less than 7. Yes, I will update. So it is at 5th index. And 5 is greater than 3. So I already get the minimum index now. So this is where my first element lies. So this is the place where my first minimum element lies. Now what I will do, I will simply swap these two numbers. So at the end of first pass, we will get something like this, which is 3, 15, 7, 8, 21 and 5. Okay. Now this is the output at the end of the first pass. Now I will consider the second pass. Okay. So now this much is sorted. So if that is the case, I will keep the pointer to the next immediate unsorted element. So now this is the place where I want to keep the next minimum element. So now what I will do, I will again reset this minimum index. So now minimum index points to 2. Okay, 1, 2, 3, 4, 5, 6. Then 7 is less than 15. Yes, so I'll update this with 3. 8 is less than 7. No. Is 21 less than 7? No. Is 5 less than 7? Yes. So I'll update this index. So it is 6 now. So I got the next minimum, I mean the index of the next minimum element. So which is 7 here. So this is my next minimum element. So what I will do, I will simply swap it. So at the end of the second pass, we get something like this. 3, 5, then comes 7, 8, 21 and 15. So at the end of the second pass, these elements are sorted and these are unsorted elements. So now I'll keep on doing. I mean for this example, I don't do it for 7 and 8 because they are already in their sorted position. So I'll skip pass 3 and pass 4. Then I'll directly go to pass 5. So now 3, 5, 7, 8, 21 and 15. So it is sorted till this position. Now we have two elements remaining. Now what I will do, I'll keep my pointer here and I'll compare with the remaining elements. So now my minimum index is 5. So I will check the remaining element, which is 15. It is less than this, so I'll update this. So now at the end of the scan, now I got the minimum element, which is at index 6. So what I will do, I will simply swap that. So my final output at the end of 5th pass, I get 3, 5, 7, 8, 15 and 21. So this is our sorted array. So this is basically how the selection sort works. So one thing what we need to understand, if at all we want to fix a particular element at any index, then I will have to scan the entire remaining elements in that particular array. So for this to be sorted, I will have to scan entire array and I'll have to find the minimum. I cannot skip anywhere in between because we don't know where exactly the minimum element exists. That's why what we need to do, we need to scan the remaining elements and then we need to find the minimum, and then we need to place that minimum element at this particular index. That is how it gets repeated for each passes. Now let us try to see its execution in a pseudocode. So I'll remove this. So what we require here. So first we need to fix the first element or the element where I want to start the sorting, or the position where I want to keep the sorted element. Okay, so for that what I will do, I will take a method selection sort. It will take some input, maybe A, which is an array of numbers. Okay, then now for this I need two loops. One loop is to see which position we want to sort, and the remaining loop is to scan the remaining elements. Okay, so for that I will take for I equal to 1, I less than or equal to n, I plus plus. Okay, now once we start, then what we need, next thing what we need is a minimum index, because we want to keep track of the minimum index. Okay, so minimum index is equal to I, because if I am starting here, I will first consider this as the minimum number. So I will assign I to minimum index. Next, for scanning the remaining elements, I need one more array. So I will take for j equal to. So what exactly we need to take the j value, the initial value? I cannot take 1 because I don't want to scan from the beginning, because the left side part is sorted. So what I will do, I will take one element after this particular I. So that will be I plus 1, and j is less than or equal to, because I want to scan all the elements, and j plus plus. Now what I will do, I will check if a of j, if it is greater than the element at min index, then what we will do, we will simply update min index equal to j. That's what we were doing when we were dry running the logic. So now once this loop executes, at the end what we get, once it is done, we get the minimum index where exactly the minimum value resides. Now if that is the case, after that what we did, we swapped the numbers. So I will swap a of I, comma a of minimum index, and we close this loop and then we close this loop. So at the end of the second loop we will get the sorted array. So this is the pseudocode for this selection sort. Now if this is the pseudocode, then what is the time complexity? So let's see the time complexity. So on naked eye, if we see, there are two for loops. So we have seen in the previous videos how to compute the time complexity for nested for loop. So on the naked eye, we can say it is of order n square. Is it really of order n square? Let's see. So what happens when, so we will check when I value is 1, how many scans happen? Scans. So there are n minus 1 scans happen, because if I am starting here, then I'll scan all these elements. So it is n minus 1. Now when it is I is 2, this is n minus 2. When I is 3, then it is n minus 3, and so on. For n minus 1th pass, there is going to be only one scan. If it is n minus 2, then it is 2. So this is how the scanning happens. So this is basically, if we sum up 1 plus 2 plus and so on till n minus 2 plus n minus 1, then this is sum of n natural numbers, so which is n into n minus 1 divided by 2, that is equal to n square minus n divided by 2. So since we consider the highest degree in this particular polynomial, it is of order n square. It is of order n square. So this is basically the time complexity of this particular selection sort. Now, what is the space complexity? So we are taking this particular variable. So this can be ignored. It takes constant amount of time, and we are manipulating this array inline. So basically this is an inline sorting algorithm. That's why there is no need of extra space. So space complexity for this one is of order 1. Why? Because we are not taking any extra space to sort these elements. So this is basically the logic and the pseudocode for this selection sort. Let's look into the selection sort execution. So I'm going to use Java and Visual Studio Code for running the program here. I have created a folder, sorting folder, and then I'm going to create a class selection sort.java. So this is the class I want to create. Then I will create a public static void method. Then after this I will create a static method which returns us the sorted integer array value, and it's a sort method, and it takes array of integer as its input. Then let us declare a variable n which gives us the length of the array. Then the first for loop, int I equal to 0, I less than n minus 1, because we need n minus 1 passes here. Then I plus plus. Then we need a variable to hold minimum index. Let it be initialized with I. Then the second for loop, int j equal to it should start from I plus 1, j less than n, j plus plus. Now we check if a of j, if it is less than the element at minimum index, then we will simply update minimum index equal to j. Once the second for loop executed, then what we will do, we will try to swap the numbers. So let us take a variable int temp, and to it you just assign a of I, then a of I is assigned with a of min index, then a of min index is assigned with the value at temp. So this is how we swap, and then once everything is run, simply return a, because this is the sorted array. Now in the main method, let us declare an array a which holds some number, say for example 21, 15, 7, 8, 3 and 5, which we saw in the dry run. Then a is equivalent to, let's call the sort method and pass a. Now let's see whether a is sorted or no. So for that we will use system dot. So before system dot we need for loop to iterate over the array. Then we can use system dot out dot print. Instead of println, let's use print, so that we will print numbers one after the other. So I will use one more print to simply add a comma and space between each number. So with this I will save and I will run this method. Let us see. So here we go, we get the sorted array. So this is how we sort using selection sort. But before closing, let's also see, is there any way we can improvise this code? Yeah, there is a little bit improvement that is possible. Here what we are doing, we are not checking whether really the min index has changed other than I or no, and we are simply swapping it, but that is not really required. First we will have to check whether the min index is really changed. So for that I will check whether I is not equivalent to min index. If that is the case, then only I will go ahead and I will swap the elements. Otherwise there is no need to swap the elements. Okay, so with this I will simply save and I'll run. We get the sorted numbers here. That's it for this video. Thanks for watching the video.